to the Power Generation, Fast Pitch, and Distribution. I'm Program Director Jenifer Shafer, and I'm really happy to welcome you here for our Fast Pitch today. Today we're going to take you through all phases of power generation and distribution. We'll be looking above ground, below ground, reuse the ground, and up to the stars eventually. And so without further ado, I'll go ahead and turn the floor over to Program Director Phil Kim and welcome you all for the show.
Scan 2.
Oh, scan 2.
Did you, question?
Yeah.
Oh, all right. I first need to figure out how to use it. Okay.
Actually, I'm probably, if I could just get the mic. Probably one more final point that I'll make is that on the back of your badges you have a QR code, and so if you can scan that as you have questions to input the questions, we'll really appreciate that. I'll be looking through them in live time.
On the same street in Anaheim, California, these two photos were taken before and after undergrounding their power lines. After undergrounding, the neighborhood looks much cleaner and more attractive. And the power outage in this neighborhood will likely be very much less frequent. My name is Philseok Kim, a program director, and I'm going to talk about new technologies that make undergrounding power lines both affordable and reliable so that we can forget about the cables. Oh, I went backward. Sorry. No. Oh, thank you. Well, these photographs of showing our infrastructure being ravaged by ever-increasing harsh weather events is becoming too common. Well, trees toppling onto the power wires are typically the problem with the power outage, but is pruning the trees really a sustainable solution to this problem? Every time there is a power outage due to bad weather, we'll see this headline, wondering why we're not burying the power lines. Undergrounding power lines involve undergrounding power lines involve too much disruption on the surface and inconvenience with the trenching and laying the conduits, burying the cables and pulling the cables, and installing underground structures like large concrete vault with manhole access for splicing the cable. And after this job is done, we have to repave the road and restore the landscape, which adds to the total cost. So this leads to the common belief that underground power systems are too expensive. And because they're not visible, it's difficult to locate the problem, and therefore it takes more time to restore the power, which means it may not solve the problem completely. Well, despite the common belief, the data tells a completely different story. This plot shows there's a trend in many European countries. The higher the percentage of the underground medium voltage power lines, the lower the SAIDI, or the SAIDI means System Average Interruption Duration Index. Where's the USA? We're here. The total SAIDI of US is over 300 minutes, and we merely have 18% of total 5.5 million miles of distribution lines currently buried. So at least can we strategically underground some of the most vulnerable power lines? In order to make that happen, it's time for us to rethink how we construct and maintain underground power systems in order to reduce the cost and improve the performance. Now, I think it's possible we can develop transformative and enabling new technologies. At the distribution level, underground power systems look just like a small version of a subway system. So we have boreholes connected by subsurface station in which we splice cable or install the taps for service for customers, and also hosting small equipment. Just like we can 3D print pretty much any shape today, can we imagine new technologies that will enable us to do underground development while leaving the surface essentially untouched? What about trenchless drilling technologies that can go through various geologic conditions with high precision steerability and rate of penetration? When we drill the hole, can we create conduits in situ? Can we construct underground structures like vault while drilling and minimize the size and numbers per mile? I believe there are lots of interesting technologies available in the oil and gas industry that we could import and apply for power industry. When we dig into the ground, there are lots and lots of surprises waiting for us, like other buried utilities. But unfortunately, today's technology is not sufficient to locate all of these obstacles. So can we develop new technologies that can map the surface underground while we are drilling so that we can avoid all kinds of hazards? The lifespan of an underground power systems is dependent on how well the installation job was done. Installation of the splice and terminations are two common causes of failure if the installation is not done right. So is there any automated machines or tools that we can use to reduce the errors during the installation of underground power systems? And after these systems are undergrounded, since they're buried, they're not visible, it's not easy to tell where potentially a failure is happening, and when the failure actually occurs, it's hard to tell exactly locate where the failure is. So are there any advanced sensing technologies that can detect and locate incipient faults? So to summarize everything here, these are the high-level key technology areas that we need to develop for reliable and low-cost underground power systems. And these things have not been done before. Subtractive and additive underground construction while mapping and avoiding all kinds of obstacles can help not only the power, but a lot of other future infrastructure upgrades and development, whether it's power, water, data, underground transportation, or low-carbon infrastructure like CO2 or hydrogen pipelines. Predicting and locating fault well in advance of catastrophic failure can not only increase the reliability and resilience of power infrastructure, but also can help other smaller systems like aircraft, ships, microgrid, solar farms, wind farms, and so on. And automated remote tools can make the splicing job faster, safer, and more reliable. And if we can develop these technologies, we may be even able to reach cost parity with legacy overhead lines at same capacity, say less than 30 minutes, which will bring the US at the top of the world in terms of reliability, and no humans on the ground for the safety of our workforce. Thank you. Now, let me introduce my colleague, Dr. Emily Yedinak, who will delve further into the Earth than I did.
Thank you, Phil. I'm a fellow here at ARPA-E, and today I'm going to be proposing my vision for white hydrogen, or geologic hydrogen, and the important role it has for the future hydrogen economy build-out. If you think about it as long as I have over the past year, you might come to the same conclusion that the Earth really is just one giant planetary georeactor. Even now, as we are sitting here in this session, trillions of chemical reactions are occurring beneath our feet, fueling the critical biological processes that underscore life as we know it, shaping the continents and mountains that we see outside this venue, and doing for free what we are investing billions to replicate, all without any intervention on our part. It was in this giant planetary georeactor that chemical reactions in an ancient primordial soup brought together atoms, molecules, heat, and electricity to form amino acids, the building blocks of proteins, and the first steps towards life. Evidence of 17 self-sustaining nuclear fission reactors occurring around 1.8 billion years ago has been found near Oklo in Gabon, Africa. And perhaps less exotic, though no less important, are the chemical reactions that every day convert carbon dioxide into sugars and underpin the global carbon cycle. Among some of the most important reactions that occur in our Earth georeactor are reactions that produce hydrogen, a critical and readily available energy source. Two of the most important reactions occur when water reacts with rock. On the one hand, radioactive decay can interact with and split water to produce hydrogen and oxygen, a process known as radiolysis. If the rock is rich in elements like iron, water will participate in an oxidation reduction reaction to produce hydrogen, a process known as serpentinization. Serpentinization has been connected with many well-known and famous gas seeps all over the world, including the ancient flames at Mount Chimera, which have been active for over 2 millennia and are purportedly the source of the first Olympic flame. I propose that this hydrogen, a byproduct of Earth's georeactor, has important implications for the hydrogen economy build-out. But first, why hydrogen? There's been a lot of hype in energy circles recently because hydrogen is often viewed as a critical chemical feedstock and a zero-carbon energy carrier for a decarbonized economy. Today, hydrogen is primarily used in chemicals refining and ammonia production, but in the future might have an important role in several industries, including synthetic fuel production, transportation, metals refining, home heating, power generation, and as a grid balancer. Hydrogen's cross-cutting utility, particularly in industries that are difficult to decarbonize, make it very attractive. However, the way that we produce hydrogen today is anything but clean. At 70 megatons per year, global hydrogen production is associated with 1.5% of the global emissions and 2% of the global primary energy demand. What's more, if we look to the future, several projections indicate that hydrogen demand will grow to be several times larger. For example, the hydrogen demand projection by the Hydrogen Council indicates a growth of nearly 8x, or essentially a doubling of the historical annual growth rate of this industry. To meet this demand without catastrophic global consequences will mean significantly scaling up both carbon capture and storage and renewable energy capacity. This scale-up can be best illustrated by two edge cases. On the one hand, if all hydrogen demand in the year 2050 alone was supplied by blue hydrogen, or hydrogen from fossil fuels with carbon capture and storage, we would need enough carbon storage for an amount equivalent to 1/5 of all of today's total global CO2 emissions, and all for this one single industry. If, however, we supply all hydrogen demand from new uses in the year 2050 by green hydrogen or hydrogen from electrolysis using renewable energy, we would need more than all of today's total global renewable energy capacity dedicated exclusively to hydrogen production. Although a future hydrogen economy scenario will likely be a combination of blue and green hydrogen, these numbers help put into perspective the truly massive scale that we need to overhaul this entire industry, and all within 30 years. What's more, if we look at the ancillary infrastructure that needs to be developed alongside a growing hydrogen market, we see a classic chicken and egg problem. Namely, low or zero emissions hydrogen production is too low or too costly to incentivize investment in hydrogen infrastructure. And the lack of hydrogen infrastructure and market access, as well as nation demand segments, preclude any increases in clean hydrogen production. Essentially, what we do today and within this decade matters. We cannot scale this industry at the expense of climate. It is here where I believe that naturally occurring hydrogen accumulations could serve an enabling role for the hydrogen economy build-out. Resource exploration in the subsurface taps into the skill set of two already massive industries, oil and gas and mining, with extensive expertise that could be leveraged to jumpstart early exploration efforts in the subsurface in the short term. If natural hydrogen accumulations are discovered and production is ramped up, they could then help unlock or de-risk investment in hydrogen infrastructure so that by the time large-scale hydrogen from electrolysis is cost competitive with hydrogen production from fossil fuels, the infrastructure and demand segments will already be in place. It is important here to emphasize that drilling into and extracting hydrogen directly from the subsurface has already been demonstrated. In 2012, a natural hydrogen accumulation containing 98% hydrogen was discovered in Mali, and has since been used to produce hydrogen to produce clean electricity for a nearby town. Similar dedicated exploration efforts like the ones that are occurring in Australia today could help uncover additional natural hydrogen accumulations, which could then be tapped into and used to produce hydrogen. What's more, if we return to this idea of the Earth as one giant planetary georeactor, we could think about potentially stimulating hydrogen-forming reactions in the subsurface to produce even more hydrogen cleanly. All this to say that if the hydrogen demand that we're projecting for the future comes to fruition, it really will be an instance of all hands on deck to make sure that we are producing hydrogen cleanly and at scale. What's more, what we do today and within this decade matters. We cannot scale this industry at the expense of climate. I propose that naturally occurring or artificially stimulated hydrogen in the subsurface could serve an enabling role for the hydrogen economy build-out. And if you have thoughts on how we can better leverage this georeactor beneath our feet, I invite you to come talk to me at Coffee with ARPA-E tomorrow morning, to write your ideas to the email listed here, or fresh and hot off the press, our request for information, which was released today. So thank you very much. And now, thank you. And now I'd like to introduce my colleague, Dr. Doug Wicks, who, much like Alice from Alice in Wonderland, found himself diving into a pretty bizarre and curious rabbit hole. So he'll be talking about gold hydrogen.
Thank you. Which one is forward? Okay, thank you very much. Good afternoon, everyone. Yes, as Emily said, I'm following her down into this rabbit hole. So Emily stimulated this idea of can we use georeactors to replace what seems like alchemy to transform stone into hydrogen as we go forward. And I hope to make a case for that as we look at this. So I want everyone to think right now about the reality of looking down at white space in a rabbit hole. This is a deep rabbit hole. The numbers get really large and very loose as we go through. So you look at this. Approximate and about are really precise terms in this talk and the way I look at this. So don't hold me to any numbers on this. And the one good thing is Google doesn't know where you're going. So when you start looking for this ideas of saying, where are you going? And Google goes, I don't know. That's the response we have to look for. And what I want to think about is iron 2 silicate. Okay, iron 2 silicate is a naturally occurring rock, which we'll be talking about, and it's Mother Nature's source of hydrogen. And basically, the reaction is you take a rock, you add water, and you get hydrogen coming off of this. And another rock, by the way. So it's a rock-to-rock transformation that gives you hydrogen as a byproduct. And Emily touched upon this. For the chemists in the group who want to have an idea of this, iron 2 silicate shown on the left reacts with water, gives you silica, iron 3 oxide or magnetite plus hydrogen. And the important thing to keep in mind is that you get roughly 6.6 kilograms of hydrogen per ton of iron 2 silicate that you react. So, where do we find these iron 2 silicates? You know, you look at this and say, well, they're found in things like olivine. These are ultramafic rocks or volcanic rocks. And they're rarely pure and never simple. But what I want to highlight on the composition of this is, first of all, iron is usually reported as oxides, even though it's actually a silicate. That olivine rocks, on average, contain about 10% iron silicates within them. So that's our reaction media. Then we have to ask, is there enough to make this matter? Will it matter if we do this? This is our key thing here we have to look at. 40% of the Earth's crust is olivine-type rocks. Think about that, 40% of the Earth's crust. And 10% of that is applicable iron minerals. So you sit down and say, okay, what does that mean? So let's pull out an envelope. I mean, this is the kind of testing we have to do. Let's look at this. And you come back. The weight of the Earth's crust, continental crust, is 10 to the 19th tons. Small little number to keep your mind on. right? 40% of this is olivinic rock. So we have 4 times 10 to the 18th tons. 10% of that is iron silicate. So you end up with 4 times 10 to the 17th tons. And you take a look at it, and you say how much hydrogen we could get 2.6 times 10 to the 15th tons of potential hydrogen. That's enough for millions of years of potential hydrogen demand that we look at. It's not a small number. So, what are we waiting for? Why don't we just go get it? I mean, this is one of those things people ask, why haven't we done this? Why don't we go do it? So, it has to be done in situ. We can't move this amount of rock around, so we've got to find ways to get down to the rock itself and do the reaction there. It's thought to be a very slow reaction. You talk to geochemists, and they talk in geologic terms. No chemist has looked at trying to accelerate this reaction, though. And their major thing is, and what impacts natural hydrogen, is there are lots of things underground that like hydrogen to eat it. It's a fuel source for bacteria and for reactions of chemistry. So where is geologic hydrogen produced? Typically, these reactions are quite deep. So these are taking place 3 to 20 kilometers underground. The question comes back, can we engineer georeactors to get down to these reactions? Can we purify and reclaim that hydrogen in an effective way as it's formed? So it also happens under fairly extreme conditions. It usually takes high temperature and pressure. This is a reaction that shows that at 1,000 degrees Celsius, which is pretty hard to get to, underground, it's fairly fast reaction, but it's 1,000 degrees. But can we catalyze it? And really, how fast is fast enough? We've got 10 to the 15th tons of this stuff to react. How fast do we really have to go? So, also what happens underground? Okay, microbes, as I said, use H2. This is a power source underground. Hydrogen also reacts with oxides and sulfides and reduces them. And hydroxide reacts with CO2 to form methane underground. These are all reactions that we have to challenge. And by the way, these are huge problems even just for the hydrogen storage issues we're going to face. So what can you guys bring to the table? So I'm out here talking to this and saying, what can you bring to the tea party? We need to be able to find and reach deep earth deposits of the proper type that will react, have the right lithology that we can get them to react cleanly. We have to figure out, how do we catalyze this reaction? How do we take it from geologic to human timescales that we can use this? And we have to find out ways to eliminate or control these parasitic hydrogen reactions deep in the ground that take place. So I want to thank you. And I want to invite all of you to say, let's reach for the end of the hydrogen rainbow. This is a kind of the series of hydrogen types that are out there. And what we want to do is really say, can we get this, what would appear to be a limitless supply of hydrogen from the Earth? And again, as Emily said, we put a FOA out on this, a request for information. If you have any great interest, ideas, crazy ideas, don't know better, or the likes, please put them in. This is a way out there idea, but with a 1% chance of success. It's a big one, even at 1%. With that, I'll say thank you, and I would like to introduce Jen.
Thank you very much for that, Doug, and thank you for taking us through the ideas and thoughts regarding being able to recover and stimulate hydrogen production from the ground. What I'm actually going to be talking about is how to take things that are already out of the ground and use them so that we can go to infinity and beyond. So nuclear energy, we know, is going to play an increasingly important role in our clean energy transition. It's low material, low CO2 need, and also as a dispatchable form of clean energy technology that will play a very important role in this transition. But we also know that there are open questions with respect to how we handle and manage the waste. But one of the things that we can be doing, and it's so obvious, is we can be recycling this. we can be recycling this material and putting it back into advanced reactors such that we limit the actual amount of waste that is produced. And there are other benefits that I'll get into later on in the presentation. One of the reasons that we can do this is because when we actually put nuclear material into a reactor, we pull it out when we've only consumed 5% of the available energy within that reactor. We've actually left 95% of that energy behind. What we have left is about 5% of it is fission products, and the other 95% is fuel that we could be putting back into reactors for generating clean electricity. Let's dig into what it looks like on the periodic table as far as what's actually in this material. First thing is that we have uranium and oxygen. This is our uranium oxide fuel that's in our current light water reactor fleet. You fission uranium, and you actually produce a whole suite of fission products, the rest of the periodic table in some respects, and that is available for a variety of different valuable trajectories. You can also produce plutonium, and this is something that can be fuel for other advanced reactors or even our current light water fleet. You produce neptunium and americium, and this could be valuable fuel for fast reactors. And so all of these elements that are generated over the course of the fission process don't necessarily represent waste, but represent opportunity that's sitting there for the taking. To think about what fission products could be used for, we know that they could be currently used for nuclear medicine applications, nuclear battery applications, and also even just classical non-radioactive things that we think about, like our noble transition metals. The intrinsic worth currently, and this is actually an old value that I have with the current values here, so not representative of recent supply chain disruptions that we've seen. But our current value of basically UNF and transition metals in our UNF is on the order of $60 billion. That value in and of itself could actually be an economic incentive to go through and recover and reprocess and recycle materials. And that's even before we get to the fuel. Let's also talk about raw materials mining requirements. We know that nuclear in general has a relatively low raw materials footprint, and it compares favorable with hydrogen, wind, et cetera. If you dig a little bit deeper into this, you can actually see that a significant amount of that mining requirement is from the uranium originally. And with that, if you take that away, then you're actually bringing this value to a much lower amount. And this is what makes me think that we can actually bring this to infinity and beyond. So basically, we have enough material actually on our Earth's surface right now in the US that we could be powering our advanced reactor fleet with materials that currently sit already mined and available for use. And this could actually bring the US nuclear industry to the post-resource world that is normally what we think about when we're talking about technologies like fusion energy, which is fundamentally disruptive in how we consider this landscape. Another interesting byproduct of this is the idea that we could actually transform this waste challenge from something that's actually a million-year challenge to something that's several hundred years. So here basically I've shown the hazard index for material with respect to natural uranium, and you see that we don't cross that line for on the order of 1 million years. If you take this material out and you take uranium, plutonium, neptunium, americium, and curium, and you actually fission this in fast reactors, it turns out that you're not talking about a million-year challenge anymore. You're talking about a challenge that's on the order of less than 500 years. And now instead of talking about an inter-civilization challenge, we're talking about an intergenerational challenge that's comparable with the waste management legacies associated with other conventional technologies. So what are the current challenges? What's the path forward? It turns out that we know that cost is something that we need to seriously consider. Reprocessing facilities don't cost on the order of millions of dollars, they're on the order of billions, at least how we currently think about them. We also know that historic technology is basically legacy from our weapons and defense architecture. And as a consequence of this, we generate pure plutonium streams, and we also don't have the current in-process monitoring that's been enabled from basically modern developments. So in order to bring this forward, ARPA-E has actually launched recently the Curie program, converting UNF, used nuclear fuel radioisotopes, into energy. When it comes to decreasing costs, there's a few things that need to be kept in mind. One is that concrete and rebar drive facility cost, and so we need to actually manage our facility volume, because we know reprocessing facilities right now aren't actually 1 football field long, but they're actually 3, and we can do this better. When it comes to actually looking at the safeguards and materials accountancy, we know that in a normal process, you don't actually do your materials accountancy until you're actually through the end and you basically count your plutonium atoms. And so there's basically a lag as far as when we actually know where the plutonium was. Instead, what we could do is look at this in considering online monitoring, where we notice immediately, as soon as material has been able to leave the pipe, how to process subset, et cetera, and we're able to predict this before we get into the materials accountancy area. And this would actually bring about not only improvements in materials accountancy, but also in operational cost and observation. And so Curie really aims to change two main paradigms regarding UNF recycling. The first one being is that reprocessing is too expensive to become commercially viable. The second one is that effective facility safeguarding only comes with additional cost with no performance value, and we know that that doesn't necessarily have to be the case. And so what we'd really like to do is take this significant resource of nearly 90,000 metric tons of material and use it to power our clean energy future. And as I mentioned, I'm Program Director Jenifer Shafer, and if you have any questions, I'm happy to talk with you about this. But speaking of post-resource worlds, I'll actually turn the floor over to Scott Sue, and he'll talk about the originator of the concept on some level.
Good afternoon, everyone. Okay, now the mic's on. Good afternoon, everyone. Thank you. It's a pleasure to follow my colleagues here. I am Scott Shu, Program Director for ARPA-E's Fusion Programs. This is not going to be a typical fast pitch, as I am concluding my stint as an ARPA-E PD. Instead, I've recently started a new role as DOE's lead fusion coordinator, and I'd like to take this opportunity to talk about fusion's bold decade ahead. A White House Fusion Summit was held 2 months ago, signaling ambition to partner with the private sector to realize at least one commercially relevant fusion pilot plant on a decadal timescale. At the event, we celebrated decades of progress and major technical achievements in fusion thanks to sustained bipartisan support. We also recognized that fusion has a unique opportunity to differentiate itself as a clean energy technology, not only in the way it uses physics, but in the way that we can engage society starting immediately to support energy justice and building a diverse workforce that looks like and benefits all of America. And then finally, we heard from the ambitious fusion private sector, who told us about their plans to develop and deliver fusion as a globally scalable, carbon-free energy source on a time scale that matters. Okay, this slide didn't quite come out right, but before I dive into fusion's bold decade ahead, I want to say how excited and proud I am of ARPA-E's fusion programs. The active portfolio now spans 40+ projects, 4 programs, and an exploratory topic, all changing what's possible in innovative fusion concepts, enabling materials and technologies, and portable diagnostics. Please come visit our fusion projects on the technology showcase floor. ARPA-E's fusion programs, along with the fusion private sector, brought a new perspective and urgency to take higher technical risk and to focus the R&D on developing fusion systems that will find customers and markets. We also proved that targeted public investments in fusion could lead to significantly greater private investments. To date, about $100 million of ARPA-E fusion investments have led to over $600 million of private investments. The bold decadal vision wants to work closely with the private sector to solve the remaining significant R&D challenges this decade, realize at least one commercially relevant fusion pilot plant, and begin commercial deployment in the 2030s, and enable aggressive commercial deployment in the 2040s. To be clear, this is very ambitious and it will be hard, but this is worth doing because game-changing innovations like fusion are the best chance for the world to reach global net zero while ensuring the U.S. can maintain its energy security and its technological leadership in the 21st century and beyond. America has a unique opportunity to accelerate fusion RD&D because the amounts of private investment enables it, indeed demands it. This plot shows that the private funding into fusion is starting to exceed DOE Fusion Energy Sciences funding in 2021. And most of this funding, the private funding, is going to American fusion companies. These impressive investment amounts are both a signal of market pull for an energy technology with the characteristics of fusion, but also of fusion's technological readiness for aggressive demonstration, aggressive development and demonstration. 2021 saw two major technical achievements in fusion, enabled by decades of sustained public support. Firstly, the National Ignition Facility at the Lawrence Livermore National Laboratory reached the cusp of ignition, where the fusion energy release was about 70% of the laser input energy. The significance here was that it gave us a second fusion approach alongside the tokamak with the scientific maturity to really motivate aggressive fusion development. Privately funded Commonwealth fusion systems demonstrated a 20 Tesla fusion scale magnet using high temperature superconductors. This represented a significant risk reduction step for their high field path to commercial fusion, leading to a $1.8 billion Series B. Please come see Commonwealth's live tech demo tomorrow at 5:30. I'm glad to say that several ARPA-E fusion projects anticipated these breakthroughs and are already building on them to enable new paths to commercial fusion. The path forward will not be easy, but it is clear. The remaining scientific and technology challenges have been well documented in expert reports over the past decade, culminating in the recent Fusion Energy Sciences Advisory Committee report, Powering the Future. Nearly simultaneously, a National Academies report laid out the key goals and innovations needed for a commercially relevant fusion pilot plant. This report recognized the opportunity to partner with the private sector to accelerate fusion RD&D, to stimulate innovation, and to spread risk among multiple teams and approaches. We are looking to successful models and examples of public-private partnership. For example, NASA's Commercial Orbital Transportation Services helped reestablish U.S. capability to deliver cargo and crew to low Earth orbit. This is one of the examples we are considering to enable the ambitious fusion private sector to innovate and move rapidly, and to have a partner with DOE all the way to deployment. Next week in DC, we will bring together many stakeholders to discuss next steps for fusion's bold decade ahead. Thank you very much. Please find me at coffee with ARPA-E tomorrow. Would love to talk with all of you and find collaboration opportunities. This will take a nation. Thank you.
Thank you very much, Scott, and thank you to all of our presenters, and thank you for all of your attention and the questions that have come in. I'll go ahead and march through things with kind of the order with which we marched through the discussion, and so I'll start with a question for you, Phil. Let's kind of scroll up here just for a moment. And so, oops, sorry, there we go. So, Phil, how do you think about that the financial incentives of investor-owned utilities to build underground power systems? So basically, financially, how do we develop a system that will encourage that? What are the tech-to-market considerations?
Yeah, this is a really tough question because utilities generally considered as the cheapest thing that people generally considered for granted. we don't want to pay a lot of money for that. But if you look at the other way, this is like rate versus tax kind of question. You know, I think there's got to be some government-wide funding to enable it. But also, utilities are currently now starting to realize that there's even more value in reliability. So the cost-benefit model has been sort of advancing by each utility, especially if you look at some of the more pressured utilities like PG&E, for example, under wildfire conditions or other areas. You know, people are starting to realize that even though its upfront cost is higher, but the total lifetime cost can be lower if they chose to underground. So these days, any greenfield development, by default, pretty much everyone will choose to underground a lot of utilities at the same time. But the remaining part where we already have overhead system, when we convert them underground, there's incurred cost. But I think how we are going to absorb it, I think it's really buried in the cost-benefit equation. So, but it's still an open discussion, and I think we will need to involve not only utilities and better technologies and lower cost technologies, and also regulators and other government. Every stakeholder has to discuss together. But for now, ARPA-E is really focused on developing technology options to enable it. But this is a good question, and hard question. Thank you.
Yeah. Thank you, Phil. Emily, is hydrogen extraction something that the oil industry is capable of piggybacking on with their current infrastructure?
So that's kind of a loaded question, right? And I think that one thing that we've discovered since diving into this rabbit hole is that the oil and gas industry is actually not looking in the right place. Hydrogen obviously is a very reactive molecule, and so you would expect that in basins that are rich in hydrocarbons, the kind that oil and gas industries typically try to target, the organic matter would actually react with any hydrogen. If there was hydrogen being produced in those basins, you're not going to see it, you're not going to observe it, it's likely being consumed in sight. So really for the oil and gas industry, they'd have to actually move to entirely different basins, ones with crystalline rocks. In that case, when we're talking about crystalline rocks, the drilling technologies are a little bit trickier, and this is something that geothermal technology developers are actually looking at extensively, right? They're developing advanced drilling to drill through some of these harder rocks to actually lower the cost of drilling through harder rocks. And so to an extent, I do believe that there is some potential for crossover, but certainly that there is an opportunity for new technologies. Of course, sensors as well as another the area that we'd need a little bit more of as well. I'm happy to talk more, but certainly there is some overlap, but certainly ways that we need to improve as well for hydrogen specifically.
Cool. Thank you so much, Emily. Doug, so this one is actually thinking about some of the technical challenges associated with your approximation discussion. So in thinking about getting water deep into some of these earthly crevices, you know, what challenges do you anticipate there, and are you already starting to pencil out what maybe solutions could look like?
You know, in the rabbit hole, there are some really good challenges. And how do you get the water down there? If you need to get the water may already be there, and just the equilibrium of the formation of hydrogen is an equilibrium reaction that lays way towards the rock. And so it might just be pulling the hydrogen out to drive it with water that's there. Otherwise, it's going to be a real challenge of how do you get water down under high pressure and high temperature. It's an engineering challenge, and we have to look at also what type of water do we do the reaction with. Do we need pure water? Can it be seawater? Can it be brines? So there's a lot of unanswered challenges in this whole.
Yeah. Scott, I'll go ahead and go over to you. So in thinking about there are many technical areas of interest, I think, still for fusion and where we could potentially move forward with this. You've spent a lot of time thinking about this. You know, what technical areas would you prioritize as far as looking after and, you know, taking on next for fusion?
Yes. Yes, there's a long list, and the only unfortunate thing is I don't have time to launch more programs at ARPA-E. But I think fundamentally, the formula to apply is taking the best science and technology and really translate that for transformative impact in fusion. And so I'll mention two examples. One is materials discovery for the extreme conditions needed in fusion, and also the economic and scaled up manufacturing of those materials. So that's one very obvious example. Especially on a decadal timescale, that becomes a very urgent problem. And then secondly is something that I actually talked about in a webinar about 1.5 years ago, and that's looking at advanced fuel cycles that avoid neutrons entirely, and this would have very significant benefits for lowering the capital cost and improving public acceptance of fusion. Just two examples, but there's many more.
Awesome, thank you so much. I'll go ahead and take a question, I guess, to self-moderating for myself. And so one thing that somebody might be interested in, as I pointed out, we're at a place where reprocessing is quite expensive, but I didn't necessarily articulate how far we need to go to get it cost competitive. And I think if somebody were to just do this as an order of magnitude estimate, I'd say you probably are in a good position if you can basically drop both your CapEx and your OpEx roughly, so capital expenditures and operational expenditures, by roughly an order of magnitude. And I think we're actually in a good position to capitalize on that. One of the reasons is that when we were originally developing these types of technologies, we were not very attentive to the wastes that were coming out of them. And obviously this has had environmental impacts, but in an interesting way, it also has direct cost impacts as far as how much it actually costs to treat and manage the material. And I think we can be much more intelligent about being attentive to that at the back end, and basically are driving our processes to minimize the waste that we need to treat. And then of course, there's been lots of advances in thinking about how we could manage and deploy operational expenses and limiting them. And so that's basically where I think there are some really ripe opportunities to innovate when it comes to reprocessing technologies. So let's see here. Phil, next question. Oh, scroll up just a little bit. No, actually. Can you clarify what percentage of US distribution lines should be underground? So also, have you thought about the challenges utilities would face in repairing those lines? So.
Yeah, well, yeah, this publication goes back to probably early 2010s. So yeah, that's we currently have 5.5 million miles of distribution lines, of which we have about 18% are undergrounded, and we're still expanding. So, and new lines are usually undergrounded, so that's good. But I don't think there's a high percentage limit that we should aim. If we can go 100%, that would be ideal. We have larger land mass and lower population density compared to many European countries. So, and this will happen over time. So we're not really undergrounding everything overnight. So, to reach reasonable level of resilience and reliability, I think every utility has their own understanding about where might be the best case to underground. But also an interesting cost model that we can think about is there's an opportunity for utilities to think about co-underground with other utilities, such as broadband. So, but this type of figuring out what would be the best has not been really not modeled yet. And I know there are people who are trying to come up with best models. So this is an interesting development. And what was the second question?
Oh, well, actually, I think I'll go ahead and move on to Emily, okay, just so that, so all right. So Emily, for you, how clean can geohydrogen be? And have you started to think about those types of production streams?
Yep, so the most common co-production gases that actually come out of a geologic hydrogen are closely associated are methane, nitrogen, and oftentimes helium, which in and of itself is actually a valuable element as well. But I don't think that there has been a national or international survey necessarily of hydrogen and the composition of the co-production gases. Oftentimes, we don't even explicitly measure for hydrogen in some of these gas seeps, and so that's a really tough question to answer. What we do know is that oftentimes the hydrogen concentration in streams can vary from day to day, even from month to month, or even within hour to hour. And I think it's going to depend on where you find hydrogen. Obviously, Mali is an unusual case where it's really pure, but we don't know enough about this resource to say whether or not that's an outlier, comparatively speaking. So to be determined. We're in active conversations with a lot of folks who are actually putting together databases of this information, but I think with more explicit efforts to measure this, we can actually better answer that question.
All right, awesome. Thank you so much. Doug, if all of the materials have already been extracted as waste rock, could hydrogen possibly be extracted feasibly from those?
Yeah, if the rock is there under the right conditions, if you were to put it into a batch reactor, you could pressurize it, add water, and increase the temperature. The question I would have is the low yield of 6.6 kilograms per ton is the logistics cost of just moving that much material into a reactor. It would probably kill the program. So I think the real challenge is to find it underground, not move it, and just pull the gas out.
Okay, awesome. Scott, so one thing that I think we've started to talk a little bit in the fusion community is about, advanced reactors overseas, internationally, things of that nature. Have you started to think about what fusion could look like worldwide aside from the US, or perhaps things too early stage to be thinking about that?
Yeah, it's definitely not too early stage to think about it. We do think, certainly to impact global emissions, we need fusion to be a worldwide deployment. And so people are thinking about, regulatory frameworks, export control frameworks, international coordination on safeguards potentially. These are all things, there's a natural tendency to want to fit fusion into fission regulations, but we don't think that's the right thing to do. Fusion has its own risk profile, and regulations and laws and international coordination should be based on fusion's risks. And we are thinking about it.
Yeah, awesome. All right, one for me. Are there other questions that the U.S. can look at when it comes to efficiently executing nuclear material recycling? And on some level, yes, on some level, no, right? So we know that France does reprocess for their nuclear fleet. That maybe one notes there is that domestically, this is not a policy decision that we've made in the U.S. to leverage basically government resources to enable this, and this is something strategically that France did. And so from that perspective, they were basically able to take infrastructure and material and say, independent of what the market looks like, we are going to basically deploy this technology with government support and get it there. So there are ways that we have seen this work, and we've seen that it work well, but I think that the market infrastructure just looks fundamentally different in the US, and so on some level, we'll need to kind of take a step back and reimagine what it could actually look like here, and there are opportunities, in my estimation, for basically how that could actually look. All right. Let's see here. Oh, maybe I'll come back to you, Phil, on the other question that that we didn't get through. Let's see here. Have you thought about the challenges utilities would face with repairing these lines, e.g. staffing, other resources?
Yeah, so repairing is also a challenge for underground structure because it's not feasible. But if we develop technologies like cable system monitoring technologies that can locate a fault or locate incipient fault, there are also other non-invasive repair technologies used in gas industry, for example, like keyhole technologies. I think this can significantly reduce the cost of repair.
Cool. All right. Emily. One thing with respect to natural hydrogen is basically, if it's there and it's available for the taking, why haven't we done it before? So, would you care speaking to that a little bit?
Yeah, I've thought about this a lot, and I think in particular in the United States, when we think subsurface, we automatically think of oil and gas and mining. I think oil and gas is maybe a better proxy for what that would look like for extracting hydrogen directly from the subsurface. And as I mentioned before, they're looking in the wrong places, and overwhelmingly, the bias that we've kind of, in talking with some folks from the oil and gas, is that it's not produced in significant enough quantities. But the fact of the matter is we've never measured it. We've never actually tried to even quantify it. There's been some estimates that have been published, and some of the estimates can be quite large, as much as a third of the hydrogen that we consume today on a yearly basis. So there's one that's like a preconceived bias in the industry, as well as where they're actually operating in. On the second side, I would say that even when hydrogen has been detected and discovered, there's a certain element that it was the side thing to the main thing. And as an example, I'll point to geothermal energy development. We've talked with a couple of folks, and they know that they actively produce hydrogen at their site, but they're focused on the geothermal energy side. They're not focused on the hydrogen. And so it's not been necessarily something where someone kind of sits back and thinks, I wonder if we can actually use this hydrogen to do something. And finally, I would just say that overall, while the reactions that Doug mentioned, and then I kind of alluded to in my talk as well, have been well studied among geologists, I think the field as a whole lacked a good engineer to come in and say, what can we practically take advantage of this process?
Makes sense. Thanks, Emily. Doug, anytime you start thinking about mining and drilling, there's naturally questions about environmental impact and things of that nature. Could you comment on that a little bit with respect to the technology that you've been proposing and thinking about here?
Yeah, I mean, the first thing you have to look at is say, this is a natural reaction. It's happening underground all the time. And it takes place, and the reaction products are quite common, not only in the subsurface, but eventually make it to the surface. So from a chemical standpoint, I'm not seeing an issue. The real challenge is going to come back, as with many subsurface stimulation systems, is do we have to stimulate so much that we could cause seismic events to take place? So that's really a key issue when we look at geothermal, oil and gas fracking, enhanced geothermal. That would have to be looked at and studied by the appropriate geologists and seismologists. So
that makes sense. Scott, as we come close to the end of our session here, when you think about the challenges and opportunities that lay for fusion ahead, so many times we think about it as, okay, this is nuclear fission, this is nuclear fusion, nuclear physics, and we need people looking at this. Where are the intersections with broader industries that you see as critical towards enabling the technology?
Sorry, I missed the last part of the question.
Just basically, what other industries, engineering technologies need to be brought to bear to bring fusion forward?
Yeah, there's going to be a lot of industries needed, depending on the fusion approach. But for example, for magnetic confinement fusion, of course, we're going to need magnet technology. So that does involve some rare materials. Just large-scale fabrication of components. I mean, we need major industry to really deploy fusion at scale. Pretty much almost anything you can think of, it's going to be needed. But I guess I would temper that with, of course, the fuel itself. Fusion does need fuel. It's just that it doesn't need very much of it compared to everything we're used to. But you will still need fuel, like, for example, lithium and deuterium.
That makes sense. And then one other question I had, which was just a quick one, is does reprocessing need to use facilities that are 3 football fields long? And absolutely not. That's one of the best ways that we could go ahead and make advances with respect to cost. And there are some technologies already that are under consideration, like pyroprocessing or fluoride volatility, that would have a significantly decreased cost footprint. And I think with that brings us to the end of our hour session. I'd really like to thank you for spending your hour with the power generation and distribution team, where we went above the ground, below the ground, reused the ground, and up to the stars. So thank you so much, and we will see you at the rest of the summit.